Hello everyone, welcome to the NPTEL course on Computational Process Design. I am Dr. Manojkumar Ramteke, and along with me my colleague Dr. Hariprasad Kodamana will be covering this course in the span of 20 to 25 lectures ahead. So in this particular course we are going to use several textbooks. The first textbook which we are going to use regularly is Systematic Methods of Chemical Process Design by Grossman, Bigler and Westerberg. In addition to this, we will be using some other reference books like Conceptual Design of Chemical Processes by Douglas, Chemical Process Design and Integration by Robin Smith, Sustainable Design through Process Integration by Mahmoud El Halwagi, and we will be using Sustainable Engineering by Bhavik Bakshi. So if we look at the design problems are of diverse natures, particularly if we take the designing of new spacecraft. Usually the new spacecraft design nobody shares to each other, and therefore designing a new spacecraft usually starts from the scratch. Similarly, if you look at the designing of a smartphone which usually have a lifetime of 2 to 3 years, in such cases the earlier model is improved based on the addition of some additional features. So compared to these designing problems, if you look at the designing of the refinery or chemical process, it has a different characteristics, primarily because if the lifetime, if you look at the uh, for the chemical process, it is usually around decades, and during this particular time period refinery processes are continuously improved or modified. So if you look at the computational process design, it involves a systematic study of translating the management level decision to the construction of the actual process plant, which can satisfy economic, environmental and social requirements. So clearly, in order to have this, the concept of several chemical engineering courses are used in this uh, um, course. So courses such as fluid mechanics, reaction engineering, mass transfer, heat transfer, process control, numerical method, process optimization, process economics and even sustainability is used in this particular course. So computational process design primarily leads to the plant construction and operation with following steps. The first step is preliminary design, then there is a detailed engineering, then the construction of the plant. After the construction of the plant, then there is a startup and commissioning. After the startup and commissioning, the operation of the plant is performed, and then the operation of the plant is continuously improved by adding the modification which is referred as debottlenecking, and at the end of the service life the plant is decommissioned. So in this case you can see that preliminary design is extremely important, because that leads to the decisions which are taken in the rest of the life cycle of the plant. So for a given chemical process, the preliminary design involves developing and evaluating the conceptual flowsheet iteratively. So there are several alternatives are present, and all these alternatives are evaluated in using the cost calculation and also the sustainability aspect. So in this case, different alternatives are obtained by rationally connecting different equipments in a process flow sheet, and then the mass and energy balance is performed, and based on that then the cost is calculated, and the best flow sheet in terms of the cost as well as the sustainability and also the operational efficiency, the best flow sheet is selected. So in order to understand this concept, let's take a simple illustrative example. So this example we have taken from this textbook, systematic method of chemical process design. So in this example, a company is producing 75 millions per year of excess ethylene stream, uh, which involves 96 mole percent ethylene, 3% propylene and 1% methane. So in this case, the objective is how we can use this excess ethylene produced for a different product which a company can sold and then earn the profit. So the head of the research team suggested that the excess ethylene production can be used for producing the ethanol, which can be sold as a product to earn the profit. So in this case, the research team is suggesting that we can produce ethanol from this excess ethylene and which can be sold. So again, the sales department has suggested to the plant manager that they can sell 1,50,000 meter cube per year of ethanol. So clearly there is a demand. Again, if you look at the typical ethanol production process, a typical ethanol production process uses the ethylene feed which has almost 99.996% purity of the ethanol feed to the reactor. But in contrast to this, in the given problem, if you look at the purity of the ethanol is 96%, and then there is a purity of the ethylene is 96%, whereas the propylene is 3% and 1% methane. So the objective here is to evaluate whether the proposed process is viable using a preliminary design or not. So now for this particular case, the main reaction is shown here. So you can see that the ethylene can react with water and that can produce ethanol. So typically this particular reaction occurs at the temperature of 535 to 575 Kelvin and at the pressure of around 69 bar. So in this reaction, the conversion, single pass conversion is around 5 to 7 mole percent. And also typically the water to ethylene ratio maintained is around 4 to 1. And this is a non-catalytic reaction which is occurring in a homogeneous condition. So since in this particular case you can see that the conversion is just 5 to 7%, and because of that large amount of ethylene is remaining unreacted, and therefore water to ethylene ratio is taken around 0.6 to 1, so that the lower molar flow rates are maintained in the flow sheet. So in addition to this main reaction, there is also another side reaction. In this side reaction, what is happening is the ethanol produced is reacting with another ethanol molecule, and that produces diethyl ether plus water as a byproduct here, okay, condensation product. So if we look at the literature, in the literature it is advised that the methane percentage in the feed should be less than 10% to avoid coking, because at the given temperature of 535 to 575 Kelvin, methane get converted to hydrogen and carbon. Again, in the reaction, trace amount of croton aldehyde is produced, and propylene in the feed reacts with the water to produce isopropanol with 0.5 to 0.7% conversion. So now we wanted to see whether this impure ethylene feed can be used in this reaction in a viable way or not. So for this given case, you can see that if we rearrange these chemicals in terms of their boiling point, so here in this particular schematic you can see that the ethylene which comprised of ethylene stream which comprised of 96% ethylene, 3% propylene and 1% propane is fed to the reactor, and along with that water is fed to the reactor, and the product coming out from the reactor comprises of several components, which includes methane, ethylene, propylene, diethyl ether, ethanol, isopropanol, water and croton aldehyde. Out of these, ethylene and water is recycled back, whereas diethyl ether is taken out as a byproduct and ethanol is taken as a product, and all other components remaining are the waste products. So here you can see that in the product line, all the products are arranged in a decreasing value, increasing value of the boiling point. So here you can see that the croton aldehyde is a solid component which has the melting point around 160 degrees Celsius. So if you look at the properties of all these components, in this case you can see that the ethylene and methane, these are having the critical temperature of 9.6 degrees Celsius and minus 82.1 degrees Celsius. So clearly these two gases are non-condensable at the given ambient temperature. And if you look at the other components like Propylene, if we look at the propylene, is having the boiling point of minus 47.7, but if we calculate the vapor pressure here, so using this Antony equation, if you calculate the vapor pressure comes around 15 atmospheric. And at this vapor pressure, if we wanted to separate propylene as a top product in the distillation unit, we have to use a condenser which can go at a very low temperature, and because of that the cost required is very high. So in comparison with this, if you wanted to separate, let's say, diethyl ether as a top product, since diethyl ether has a having a boiling point 34.6, which is very close to the ambient temperature, even the naturally available cold water can be used as a cooling agent, which is a viable option. So with this information, uh, one can see that methane and ethylene can be taken as a non-condensable gases at ambient condition, and uh, diethyl ether can be separated in a distillation column. So in addition to that, there are other components like water, ethanol and isopropanol. So water, if you look at water, uh, ethanol and uh, isopropanol, these have the boiling points which are significantly higher compared to the ambient temperature, so they can be separated as a liquid. So, and croton aldehyde is a solid component which is having a melting point of 160 degrees Celsius. So this data is taken from this book, source is mentioned here. So if you look at the literature for a given reaction, if you are using a feed of 99.996% pure ethylene, then the typical flow sheet given in the literature is shown here. So here you can see that the ethylene is first compressed to a desired pressure of 69 bar. It is mixed with the water and then it is charged to the reactor. In the reactor, the temperature is maintained around 535 to 575 Kelvin, and in at this condition, the conversion of ethylene to ethanol is around 5 to 7%, and then the product gas coming out from the reactor is then cooled down in a heat exchanger to recover the heat, and this cooled feed then separated in a flash unit, where the vapor coming out from the flash unit actually comprises of ethylene, diethyl ether and ethanol. This gas mixture is then scrubbed in the absorber by using the water. So in this absorber, diethyl ether and ethanol from the gas is scrubbed and it is taken out by the water stream, and whereas the gas separated here will be comprised of ethylene and contaminants. So this particular gas is again undergo the splitter, where the ethylene is separated, whereas the some amount of ethylene and contaminants are separated as a purge, whereas the ethylene coming out from the splitter is then again compressed in the compressor to increase the pressure up to 69 bar, which is same as the pressure required in the reactor. And once the gas is pressurized, it is mixed with the feed here, and the feed is then charged to the reactor. Again, in the flash unit, the liquid coming out from the flash unit actually comprises of water, diethyl ether, ethanol and croton aldehyde. So this stream is then mixed with the water stream which is coming from the absorber, and this mixed stream is then fed to the distillation unit. In this first distillation unit, primarily water and croton aldehyde is separated as a bottom product, whereas the top product is then passed to the second distillation unit, where diethyl ether is separated, and again the bottom product coming from the distillation unit is then charged to the third distillation unit, where primarily the ethanol is separated as a top product and the remaining water is removed as a bottom product. So this is the typical flow sheet of conversion of uh, uh, ethylene to ethanol, when the purity of the ethylene is around 99.996%. Now the question here is how we can modify this particular flow sheet for a given feed condition. So remember that in a case study, the given feed has 96 mole percent ethylene, 3% propylene and 1% methane. So it's not 99.996% pure ethylene. So clearly one has to modify this particular flow sheet in order to handle a impure feed. So what are the different options or alternatives to do that? That is what we are going to look at in this slide. So the first option is either we can separate propylene and methane, and then in the separator, and then the pure ethylene can be charged to the reactor, and the same flow sheet can be used um, uh, for the production of the ethanol. So that is the option one. So in this option, however, if you look at the, if you wanted to separate, let's say, methane and ethylene. So remember, the feed available in the plant has 96% ethylene and 1% methane. So if you wanted to separate this methane from this ethylene, if you look at the boiling point of the methane, so if you look at this particular table, the methane has a boiling point of minus 161.5 and the critical temperature of minus 82.1. So clearly, if I wanted to separate this methane from ethylene, uh, in the distillation process, the methane will come out as a top product, but this top product has to condense, and then the reflux has to be charged to the distillation column, isn't it? So clearly we require to liquefy the methane, and which require a heavy duty condenser, and which is not a viable option in this case, since the critical temperature of the methane is minus 81.2 degrees Celsius. So another option could be we can separate the methane and uh, ethylene by using a membrane separator. So in this case, the feed has to be charged to the membrane with a high pressure, and the methane will be separated at a permeate side. So clearly there is a chance that some of the ethylene will uh, uh, pass to the permeate side, isn't it? So there will be a loss of ethylene on a permeate side. So this option is also involves a cost. So another option could be we can directly charge this methane to the reactor instead of separating, and allow the amount of methane to build up in the reactor up to 10 mole percent. As the problem given here, you can see that up to 10 mole percent we can use the methane in the feed without coking. So we can feed the methane to the reactor directly instead of separating, and we can allow it to build up, and we have to make sure that the amount of methane in the feed should not go beyond 10%, and then the methane can be removed from the product stream as a purge, isn't it? So and remember, the product coming out from the reactor is then sent to the flash unit. You can see that it is sent to the flash unit, where the ethylene diethyl ether and ethanol is sent to the absorber, where diethyl ether and ethanol is separated by using the water. So here you can see that ethylene and methane will be there. That methane will be, some amount of methane will be separated here in the purge unit, in the splitter unit. So that is the option number 2. Similar to methane, there is another impurity which the feed is having, and that another impurity is the propylene. Now if we wanted to remove, let's say, the propylene before feeding it to the reactor using the separator, using, let's say, distillation, so this is also a costlier uh, option, primarily because if you look at the propylene, propylene has the boiling point of minus 47.7 degrees Celsius. So clearly, if you wanted to separate the propylene from the ethylene feed, we have to use the condenser which can liquefy the propylene at minus 47.7 degrees Celsius, and which will cost a huge amount of money. So clearly this is not a viable option. Also we can look at another option of separating the propylene using membranes. So if we use the membranes for separating the propylene, in that case, the propylene will be on the one side, and the ethylene will be on the permeate side. So clearly the ethylene which is coming out from the permeate side will have a low pressure, and this particular stream has to be pressurized to 69 bar, which is the required pressure in the reactor. So clearly the compression cost is going to be very high in this particular option. So clearly separating the propylene is also is not a viable option by using the membranes. So in this case we can send the propylene also in the reactor similar to methane. So if the propylene is sent as a reactant in the reactor, in that case it get converted to a isopropanol by reacting it with the water, and this isopropanol we can separate in the distillation column later. The only challenge here is this isopropanol has the boiling point uh, 4 degree higher than the ethanol, so which will have some difficulty, but still we can separate it. So one can see that with respect to the impure feed, we have several challenges and there are several alternatives which we have to evaluate iteratively using the flow sheet synthesis in a systematic manner while ensuring the economic viability and sustainability. So if we look at the flow sheet synthesis, so flow sheet synthesis is the process of designing and optimizing a schematic representation of a chemical process. Process design is a critical aspect of chemical engineering, shaping the efficiency and economic viability of the processes. It is essential for mapping out the entire process and identifying the optimization opportunities. So you can see that any process, any chemical process can be generically represented using the process flow diagram as shown here in this slide. So raw material can be charged to the reactor feed preparation, and from here the reactant is then charged to the reactor. From reactor, then the product coming out from the reactor is then prepared for the separation, and this uh, product stream is then passed to the separator where the products are separated, and some of the products then again can react in the reactor, which are again separated in the subsequent steps, and some of the reactants which are removed in the separator are recycled back to the feed. So if you look at this particular generic flow diagram, we can map the given flow sheet in the generic flow diagram as well. So you can see that in this case ethylene and water, so here ethylene is first compressed and they are mixed. So all these initial feed preparation unit we can consider these. So you can see that reactor feed preparation units in this case will be compressor and mixer. Once that is done, the mixer is then charged to the reactor. From the reactor, then the hot product stream is exchanging heat with the heat exchanger. So you can see that the separator feed preparation unit in this case will be a heat exchanger, or even the flash drum, so flash unit. Okay. So and subsequent separators will be the distillation units from where the products will be taken out, and the unreacted ethylene and water can be recycled back. So if you look at the process synthesis design, the typical block diagram one can have is the raw material is coming into the process flow sheet and the products are coming out. So process flow sheet synthesis actually is nothing but the method to determine a process flow sheet that satisfies all product, operational and other requirements. So a flow sheet typically includes symbols and representation of the equipment, pipes, valves, instruments and material to illustrate how a process operates. The primary purpose of the flow sheets is to provide a visual framework for understanding the process, optimizing it and facilitating the communication among the team members. Again, the flow sheets are used in various industries such as chemical plants, oil refineries and food processing units. So we will be looking at how we can generate the preliminary flow sheets, and these preliminary flow sheets we can refine iteratively by using the alternatives available. So while obtaining the flow sheets, the key objectives that need to be satisfied are optimization of the process. So which whenever we are generating the flow sheets, we aim to optimize the entire process to maximize the efficiency and the performance. Another key objective which is used while generating the flow sheets is the cost minimization. So we wanted to minimize both capital and the operating cost associated with the process. The another objective which is considered while generating the flow sheets are the resource efficiency. So we wanted to use the energy, raw material and time judiciously while generating the process flow sheets. We also wanted to maintain the product quality and yield improvement, and while maintaining the safety standards. Also environmental impact reduction is required, so we aim to reduce the environmental footprint, including the waste generation and emissions. So this particular aspect is extremely important in current scenario, where the process flow sheets are not only generated only based on the economic viability, but also the sustainability in terms of the environmental protection as well as the societal requirement. So the last important objective that need to be satisfied while generating the process flow sheet is flexibility and adaptability. So clearly you can see that if you see the timeline of refineries or process plant, that spans for decades. So clearly the process should be designed in such a way that it can adapt the changing conditions and market demand. So if you look at the basic steps involved in flowsheet synthesis, so there are 8 different steps involved. So first step is to collect the data and analysis. So we can collect the experimental data, process specification and material properties. So depending on the management decision, based on the management decision, we can collect the experimental data and the process specification from the literature, from different encyclopedias or from different online resources, and based on that, uh, then we can outline the process unit operations and their connections in the flow sheet. So based on that, the preliminary flow sheet is made. uh, Again, in this we have to select the equipments. So we can select the equipment for each unit operation considering the capacity and the efficiency. Once this preliminary flow sheet is generated, then we can do a material and energy balance, and based on the material and energy balance, then we can calculate the cost for this preliminary flow sheet. Once this preliminary flow sheet is generated, this preliminary flow sheet is then refined by using the different simulation softwares. Again we can iteratively modify these preliminary flow sheets based on the different options available, alternatives available. And once all these steps are done, finally we conclude with the development of final optimized flow sheets that align with the project objectives. So these are the 8 different steps involved in the evolution of the flow sheet synthesis. So let's look at what are the different alternatives present and how, in the context of the given illustrative example. So again, as I said, that the preliminary design is extremely important, primarily because even though the cost involved in the preliminary design is around 50 to 20% of the total cost, however it has the impact on the remaining 80% of the cost which is occurring over the lifetime of uh, the process. So here you can see that whatever the decision we make in the preliminary design has a significant role in shaping the operation of uh, the process. For instance, very often if we do the preliminary design in a uh, uh, non-optimized manner, it may possible that the obtained design is giving you a bad performance, but actually the given option or a given decision, management decision, may be actually beneficial. Okay, sometimes the design is such that every time the plant has to revamp or modify in order to remain competitive. So all these preliminary design decisions have an impact throughout the lifetime of the process. So again, let's look at the different alternatives those are possible for the given illustrative example. So this is the same illustrative example where ethanol is produced from ethylene. So in this case, uh, you can see that this particular flow sheet we can represent in a simpler way by aggregating the equipment. So here you can see that all feed preparation equipment we can aggregate in one block. Then the reactor is aggregated in one block, and all the separation units are aggregated in the last block. So these 3 blocks are representing the entire process. Such simpler representation very often is used to communicate the information concisely to the team members. Again, this equipment aggregation can further be simplified only in terms of one block. So here you can see that the complete process is shown where the inputs are there and there are certain outputs are there. So now let's look at what are the different alternatives present in the given flow sheet. So for the same ethanol production flow sheet, remember that we can either separate the uh, propylene and methane from the feed and then charge the pure ethylene to the reactor. So this is the alternative one, where you can see that the ethylene, propylene and methane feed is given to the separator, where the propylene and methane is separated and the pure ethylene is then charged to the reactor, and in this reactor then water is added and the reaction is occurring, and then the product coming out from the reaction will be comprising of ethylene, diethyl ether, ethanol, water, cotonaldehyde, and from this mixture we can get the ethanol as a product, we can get the ethyl ether as a byproduct, we can recycle ethylene and water back to the reactor, and cotonaldehyde, which is a solid component, which is separated here. So this is one alternative. Of course, in a similar manner there are different possible alternatives. Another such alternative is instead of separating the propylene and methane before the reaction, we are directly feeding the propylene and methane along with the ethylene to the reactor. So here you can see that the product stream will be comprising of methane, ethylene, propylene, diethyl ether, ethanol, water, cotonaldehyde. So clearly we have to separate cotonaldehyde, propylene, methane, isopropanol here, and diethyl ether will be taken as a byproduct, ethanol will be taken as a product, and then ethylene and water will be recycled back to the reactor. So these are the two alternatives we have shown, but in a similar manner there are multiple alternatives are possible. For instance, in this case we may select the option of separating propylene but not methane. Similarly, there could be another option where we are separating methane but not propylene. So there are multiple options are there, and with respect to all these alternate routes, one has to see which route is viable by using the cost calculation. So once the route is represented as a process flow sheet like this, then the material and energy balance is performed, and for this preliminary material and energy balance, the preliminary calculations can be performed to find out the cost, and if the cost comes out to be reasonable, and if the profit is outweighing the cost, in that case one can go with the given design for further refinement. So similar to the alternate route in terms of the feed of the reactant, the alternate routes can be represented if the process flow sheet is represented in the form of task. So in this particular slide you can see that the entire flow sheet is represented in the terms of task. For instance, if I look at this particular flow sheet, here you can see that the water and ethylene is compressed and then heated before it is charged to the reactor. So here the task could be increase the pressure, increase the temperature. So that is what is shown here. You can see change in P, change in T. So this is with respect to, let's say, ethylene. Similarly, with respect to water, change in P, change in T with respect to water, and both of these are then mixed here. After that, this mixture is charged to the reactor where change in the space is taking place, so reaction is occurring, and because of that the new components are formed. So change in the species is the next task. Then the product coming out from the reactor is then exchanges heat with the water uh, 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 to recover the heat generated during the reaction. So for that, change in P and change in T will be performed in the flash unit as well as in the heat exchanger, and finally the cooled product stream is then separated in the distillation column to remove the product as well as the waste products. So you can see that the entire flow sheet which we have shown here is converted to a another diagram in the form of task. So now if we represent the given flow sheet in the form of task, then we have several alternatives present here. For instance, what should be the range of P, what should be the range of T, all these changes is going to give us the large number of alternatives possible, and based on all these alternatives one has to select the best alternative which can give uh, the highest profitability. So similar to the task, again the process system can be represented in the form of heat exchanger. So remember, in this case, some streams are losing the heat, some streams are gaining the heat, and if we represent the temperature as well as the heat flow for the entire system, we can actually find out what is the lowest amount of utilities required for the process. And that is very important, because the amount of utility will incur the cost. So such representation is also useful to find out the best alternative possible. Again, not just in terms of the temperature and the heat, but also in terms of the composition. We can represent the entire system in terms of change in the composition, and one of such representation is a McCabe-Thiele diagram, isn't it? So where we can find out which will be the feed tray, etc. Okay. So clearly such representation can give different alternatives, and not just the alternatives, but also very often it gives what type of equipment can be used for a particular separation task. So once this is done, then once the different alternatives are uh, generated, then one has to assess the results with respect to all these alternatives, and based on that we have to select the best alternative among the possible alternatives. So here we can assess the results in terms of different criteria. The first criteria is the economic evaluation. So in the economic evaluation, a preliminary design requires establishing the cost of the equipment and the cost associated with purchasing the utilities. These methods assume that mass and energy balances have been completed, and once this is done, then we are going to select a particular preliminary design which is giving the lowest cost. The next assessing criteria is the environmental regulation. So it emphasizes the importance of complying with the various government regulations related to air, water and land pollution. The next assessing criteria is a safety analysis. So highlights the necessity of conducting the hazard studies to identify and mitigate the process standards in order to make the given process safe operationally. Then process flexibility, this is a very important criteria, primarily because if you look at the chemical processes get modified over its lifetime. So depending on the dynamic conditions present outside, so need for processes to adapt to variations in input and operating conditions using and the classic example here is the petroleum refinery, where the feed from different location can come in. Sometimes the prices or demand are varying significantly. In such dynamic environment, whether the process is going to adapt will be able to adapt or not is important factor. The last assessing factor is a controllability. So clearly it addresses the challenges of maintaining process stability during dynamic changes and disturbances. As I said, very often what happens is, if you take an example of crude oil um, fractionation, so sometimes the crude oil arrival get delayed. Sometimes you can see that the pump failure is there, so because of that some tank is unavailable for feeding the distillation unit. Sometimes a particular distillation unit has some problem, isn't it? So in such cases, in such dynamic environment, whether the process is stable or not, okay, so that is referred as a controllability. So next we are going to look at how we can generate the process flow sheet, how we can synthesize the process flow sheet in a systematic manner. We stop here. Thank you.